Or not phase.
Oh, phase. Okay. That it's actually defining the phase. That's important. Why else might that one stand out? Say that again? It's an acid. We have the hydrogen in front and we have the aqueous in back, which is suggesting that we have an acid. Right? Why would we identify that and name that differently than the other compounds? Before you took this class, how many of you thought acids were dangerous? Oh, okay. You already have some of that context. Right? You have some of that context because acids and ultimately bases already had some inherent safety issues. So those things get trained into people very early on in their lives, whether or not they've learned anything about chemistry beyond that. Okay? So we call attention to it. Okay? Why might we call attention to it? Okay, this is where I would reference observationalists, so not necessarily scientists, but probably the beginnings of scientists, people just making observations about things. Okay? And they noted that there were certain materials that had different properties. Right? Like I have this container of a clear liquid, and when I stick my hand in it, it burns and all the skin melts off. I might want to label that so that nobody else does the same thing. Okay? And what I might label it, interestingly enough, is corrosive. Okay? I have another container of a clear liquid in it. I stuck my hand in that one, and because it wasn't labeled corrosive, I didn't stick it. It was like, it's okay to stick my hand in it. It's just water, right? If I stick my hand in that one, my skin also melts off. Okay? So I might go through and label that corrosive. But if two containers are labeled the same thing, what might we do with those two separate containers? We might mix them. We might say they're the same thing. Okay? So I mix them. Okay? At this point, I'm already nervous because my hands have both melted off. So I tell somebody else to mix them for me. And when they mix them, it reacts very violently, okay, boils, and now they're splashed head to toe in a mixture of boiling, corrosive, and this other thing. Okay? So now I'm like, well, I'm missing both hands. I just mortally wounded a colleague of mine. I want to make sure that that other thing is not labeled the same. It did the same thing, ultimately, to my hand, but if I label it the same, what happens? We mix them, and that was also dangerous. So we come up with a new word. That new word, caustic. So if you look at the hazards for these two substances, typically one is called corrosive and the other one's called caustic. What is the difference between corrosive and caustic? Pretty much nothing. They both do the same thing. But we came up with a different term to reference those hazards so that we don't get the idea of, okay, it's okay to mix or even keep those stored in the same place. Because if I mix them, it becomes another issue. Kind of makes sense? All right, so language, fun thing. With that kind of corrosive substance, because at this point I've melted off my hands, I'm starting to make somebody else experiment. And when I make somebody else taste it, they notice that it tastes sour. They didn't lose their tongue, but hey, it tastes sour. Okay? The whole time my skin was melting, it kind of felt sticky. Okay? So we've got classifications on those. Okay? That response of the hand melting or the skin melting off or my tongue falling out, okay? All of those are kind of extreme cases. What we're looking at in those cases would be the super strong acids as opposed to weaker acids. Weaker acids are going to have this nice kind of sour taste, like a lemon. Why does a lemon taste sour?
Citric acid.
Citric acid. There is an acid within the lemon. Okay? So what we're looking at is classifying those substances according to their kind of bulk properties. Acids tend to be sour tasting, sticky feeling, and corrosive. Bases, on the other hand, tend to be bitter tasting. Okay? Maybe you all aren't old enough to be at that level or still have parents that are torturing enough. You ever swore when you were a little kid and your parents said they were going to clean out your mouth with soap and that tasted awfully soapy. Bitter. Why? What is soap? Soap is a base. Okay? So just like with acids, bases don't have to like melt off your skin. Okay? We can come up with some of those bulk classifications, so we get bitter tasting behind those. Also a slippery feeling as opposed to a sticky feeling. Okay? Why is it a slippery feeling? It's reacting with the fat on your skin, the oils on your skin, to make soap. Okay? So it's turning your skin into soap. That's why you get the slippery feeling. Okay? And they're also kind of caustic. Again, we have to be concerned about levels. I'm not saying stop using soap. Okay? Soap is a mild base. It's not doing that super reactivity aspect of our strong bases. Okay? So we've got these kind of big observations. We know they're dangerous, so we want to call attention to them. That's where we come up with the different hazard names, and we come up with different names for those particular compounds, acids and bases. When an acid reacts with a base, okay, after I let it react and chill and stop boiling and being violent and scary, and I stick my hand in it, then what happens? Nothing. So these two things that were insanely dangerous, when I now mix them with each other, they make another massive, crazy mixture thing going on. But when that crazy mixture settles down and I stick my hand in, nothing. Okay? What happened to the acid and the base? They were neutralized. So we can call that a neutralization reaction. So if we look at the basics of the reaction shown here, we're starting with, and I know you don't call me out on the aqueous, we're starting with an acid, mixing it with a base, and the end result of that reaction is I form water and a salt. Okay? The salt is typically neutral, not really dangerous, and we end up having canceled out the reactivity of those compounds. Okay? Why don't we just call it a double replacement? Well, for the same reason we call these acids and bases. That chemistry is so old and so particularly unique that we call it by its own reaction name. It is still a double replacement. It's just better to call it a neutralization. Okay? A square is still a rectangle. Why do I call it a square?
Because it's very specific.
It's a special rectangle where all the sides are now the same. Okay? So we're just kind of doing nuances within those rules because there's special things that go along with them. Okay? Because we had this chemistry, we then tried to come up with ways to classify them and identify them. So Arrhenius was the first one to go through and come up with definitions for our acids and our bases. Okay? His definition for an acid said that when we added that acid to water, we noticed an increase in the concentration of hydrogen ions. Okay? Well, hydrogen ion is the H+. You might hear that referred to as a proton. Why would we call that a proton?
It doesn't have any neutrons.
Okay. A hydrogen atom has one proton, one electron. How many neutrons? None. So if I look at the hydrogen ion, what have I done? I've removed an electron, and so the only thing left is a proton. So we can refer to the hydrogen ion as a proton. When we're looking at the acid-base reaction, okay, say the neutralization, actually back here, we're not talking about adding a proton to the nucleus of our atoms. We're talking about adding a hydrogen atom that now hangs out outside our structure. Okay, so this isn't nuclear chemistry when we're referring to it as a proton. We're just saying it kind of exists out there. When we look at bases, bases when added to water increase the concentration of hydroxide. Okay. So what would I look for in an acid? Hydrogen. Does CH4 have hydrogen? Is it an acid? No. Why is it not an acid?
Isn't an acid that always has a hydrogen in front?
Right. Our rule for this class, okay, and it's a really crappy rule, but it works, so don't worry about it. It needs to have the hydrogen in front. Okay, why? Because we aren't explaining to you the basics of why those bonds are breaking and forming. We're just saying they do. If we don't explain to you why they're happening, we can't expect you to look at that structure and know that that bond will not break. Does that make sense? So we'd have to call attention to it by putting that hydrogen out front. Make sense? All right, so we're looking for that hydrogen in front. What are we looking for a base? Okay. OH isn't a bad idea. So let's always, just like we did with the CH4, let's throw in another example. CH3OH, a base.
And you need a cation and an anion?
We need a cation anion. So when you say OH, it's not OH. You're referencing hydroxide. Hydroxide is OH minus. To be negatively charged, what must it be bound to? A positive charge. What things are positive? Try that again. Metals. It has to be bound to a metal for it to be a base. So when we look at CH3OH, yes, there's an OH, but that OH, not hydroxide. Anybody process that one? Seems kind of weird, doesn't it? Okay. That OH is not hydroxide. Okay. Why? Because that oxygen is bound to carbon. Carbon and oxygen share electrons through a covalent type bond, which means we don't form a negative charge. No negative charge, no hydroxide. So CH3OH, not a base. Kind of, sort of? So when we're looking for our bases, we're looking for the presence of hydroxide, which is that negative. The easiest way to get that is attach it to a metal. When we're looking at acids, we want the hydrogen out in front. That's probably good enough, but officially we should also see the aqueous. In both of these circumstances, the aqueous almost becomes implied for the Arrhenius definition, because when are these definitions true? When they're dissolved in water. Right? If they're dissolved in water, by definition, they're all aqueous. Okay? These definitions on dealing with the change of either hydrogen ion or hydroxide ion are huge and vastly important. Okay? Why might we have zeroed in on those two particular ions? Why might I have kept my focus on those two ions?
Because they make water.
Mixed together, we have water. Why would water be such an important thing to reference? It is a product, yeah.
It neutralizes.
It neutralizes, yes.
We need water and life to do.
Water makes up 70-80% of all life as we know it. Without water, we don't exist. Water's kind of our center point for all of our reactions. Okay? When we're studying chemistry, we're concerned about the presence of water because that's where all of our chemistry happens. Okay? So that's why the focus initially went to water. And when we split water, we get hydrogen ion and hydroxide ion. Kind of makes sense? Okay. If you are lucky enough to continue through chemistry, you'll move into 152 eventually. And in 152, you spend a vast majority of your time dealing with this reaction at the bottom. The relationship between hydrogen ion, hydroxide ion, and water. It's how important that is. Okay? You spend a huge amount of time dealing with that. And it becomes a little bit more challenging, okay? Potentially more interesting if you're into that kind of stuff. Okay? If you get even more lucky and you continue to move through chemistry, you move into organic chemistry, and we don't like water because water, it does ruin a lot of things. But water's not organic. For it to be organic, it needs to have carbon and ultimately hydrogen. It needs both. Okay? So depending on where we're looking, we'll adjust our definitions, which is why we get the next thing. If you've looked at the slides, being an organic chemist, I think these definitions are pretty useless. These definitions are way too narrow to be applicable. They only apply to the presence of hydroxide ion and hydrogen ion. There's a lot of other reactions out there that don't involve hydroxide ion, okay, but could still be classified as bases. So a second definition was determined. This is the Bronsted-Lowry definition. Okay? So what Bronsted and Lowry went through and did is they just kind of separated it, and they decided to look at it as the transfer of the hydrogen ion. So they kept their focus on the hydrogen. Acids will donate H+, or our hydrogen ion. What do bases do in the course of a reaction? Remember, our focus now is not on H+ and hydroxide. It's only on H+. What must the base do? The base will accept H+. This broadens the definition ever so slightly, and it broadens it enough that in organic chemistry we use the Bronsted-Lowry definition and we entirely ignore Arrhenius. Okay? Because in the Bronsted-Lowry, does it say anything about water? No. Most of the reactions that we run that are acid-base don't have water in OChem, so we use a definition that doesn't incorporate water. This definition in and of itself is also very, very narrow. Okay, so we expand it even further. You remember Lewis electron dot theory, coming up with structures? Well, Lewis also came up with another definition for acids and bases. Okay? That definition of acids and bases is now so broad that it's not useful. The Lewis theory goes through and explains virtually all chemistry by looking at the transfer of electrons, not the transfer of an atom. Okay? Why might that be challenging from a student's perspective? Let's take a look at a standard chemical equation, right? We've been looking at those a lot, right? Does everybody see that the hydrogen has changed locations? Yeah, hydrogen out front. This hydrogen, instead of being bonded to chlorine, is now bonded to...
You're not writing anything.
Yeah, he is. Yeah, he is. It's on top of. I blame the projectors. Is that more visible? Our hydrogen has changed locations. Instead of being bonded to the chlorine, it's now bonded to the nitrogen. Okay? The sodium floats off, and we pretty much ignore the sodium. Okay? For those of you in at least one of the lab sections, scratch that, you didn't do that lab, might know what we would call sodium. I skip this topic in lecture and leave it for lab because I just find it irritating. Any idea what we might call sodium? It's a spectator ion. Why? If we go through and address phases, that one's aqueous, this one's aqueous. Sodium chloride is aqueous. NH3 is a liquid. So if we were to go through and look to see where the chemistry occurred, did sodium actually do any chemistry? It started in a compound that was aqueous and it ends in a compound that was aqueous. Did we change the phase? No. So because of that, sodium didn't do anything. We can reference it as a spectator ion. Chloride is in a similar boat. Okay? So if we focus on just the chemistry of those atoms, we can see how those things changed. Kind of, sort of? Okay. So there's our Bronsted-Lowry definition. Lewis expands it a little bit further by referencing electrons. Again, why are electrons challenging? Ooh, someone said it.
Can't see them.
You can't see them. When we look at that chemical equation, where are the electrons? Where did I write electrons? I didn't. Okay? Those electrons become implied in those formulas. Okay? So the Lewis theory, while it applies to everything, really only works when you start looking at structures. We haven't evaluated anything to do with these structures. Okay? Why would structures become more important? When we draw out a structure, what do we also draw? Begins with a B. bonds. And what are bonds? Electrons. So when we have a structure, we can use Lewis theory a little bit better. If we don't have a structure, we can't use Lewis theory as adequately or as appropriately because we don't see those electrons. So it's harder for us to recognize that pattern. If you have to move up into OChem, that is the hardest part of OChem, is recognizing that a formula still has electrons. Those electrons have to do all the chemistry. Okay? So, hydrogen ion donor was our acid. Our hydrogen ion acceptor is base. This is tied to which definition? Our Bronsted-Lowry. Almost always it's written as Bronsted. Okay. And if you want to get extra precise, officially Bronsted, I believe, I could be wrong on this, should have the 2 dots. What is it? The umlaut? Umlaut. 2 dots above the oxygen. So the pronunciation gets weird. That's about all I know. Okay? So the next big thing that comes out of this is our conjugate acids and bases. So let's keep focus at the top reaction. At least top reaction first. What do you think SO3 minus 2 will act as? Acid or a base? Why do you want to say a base?
Because acid accepts.
It doesn't have hydrogen.
Right? This is where our definitions can really come in handy when we're looking at acids and bases. Our definition for an acid meant
Has to accept that.
Donate.
it has to be able to donate hydrogen. Does SO3 minus 2 have hydrogen to donate? No. Which means can't be an acid, it must be the base. Okay? When we switch to acid-base reactions, one of the things that we're going to do is only transfer 1 atom at a time. We won't do multiple atoms. So if I run that reaction, okay, and I have that act as a base, I am going to end up with SO3 again on this side, but it will have accepted a hydrogen. So the formula becomes H, SO3. What charge would it be?
Negative.
Why is it negatively charged?
Because SO3 is -2 and hydrogen is +1.
All right, we have to look at our balance of charges. SO3 was a -2 charge. We're looking at the sulfite ion. If it accepts a hydrogen ions are positive. 1 positive cancels 1 negative, and I'd be left with HSO3 minus. Good? Okay. So what we did was moved from the base on the left-hand side to this structure. Okay. Where did it get that hydrogen from? That got that from the H3O plus. Okay. So what is the other product? We'll end up with H2O. What charge should it be?
Neutral.
Why is it neutral?
Because the oxygen has -2 and there's 2 hydrogens.
Fair enough, I'll accept that. Looking at our oxidation states, okay, we could apply that. The other option, we started with a positive charge. What did it lose? What did it lose? H plus. So it loses a positive. If a positively charged structure loses a single positive, what does it become? Neutral. Everybody good with that? Okay, so now the fun part. What is different about this reaction than any of the reactions we've seen so far this semester? What?
You don't do it like
The arrows. What do you mean the arrows?
Says both ways.
Right there in the middle. We're used to seeing one way. Guess what? Very rarely are reactions actually one way. They actually go both directions. Right? Which means depending on how you look at that reaction, it could be going left to right. It could also be going right to left. Okay, so let's look at the right to left. What happens to HSO3 minus to go from the right to the left?
And considers it acid.
It loses a hydrogen, or it donates a hydrogen, which means it is acting as an acid. What's that?
You just flipped it for either way.
Okay, what happened to the water? It accepted the hydrogen, which means the water is acting as a base. Awesome. Questions about that? You all good? Okay, that's cool. I'm fine with that. Go for it.
You said acting as a base. Why is that even?
So again, remember, we're now changing our reading. Everything we've done is reading left to right. I'm now saying stop it. Read right to left. Water becomes which of these two species? SO3 minus 2 or H3O plus? H3O plus. What happened to water to become H3O plus? It accepted another hydrogen. If it accepts a hydrogen, what is it? A base. Okay? So we solid on that?
I have a question.
Yeah.
So the reason why the arrows are facing both ways, it doesn't make it a double replacement
No.
because of the arrows?
Nope. The double replacement is only referencing the exchange of two ions. Okay? In this case, it is a double replacement. It has nothing to do with the arrows.
Okay.
Entirely separate piece of information. Other questions on what's up there? Identify the base. There was a statement for you to identify the base.
Depends on which way you're going.
Okay? So the quick response is, that sounds like a trick question, because we have two things labeled as bases. So depending on which way the question is referencing, we would change the answer. Okay? That could lead to an awful lot of mistakes, ultimately, because there's confusion. So how do we prevent that confusion? Okay. There are 3 Michaels in this room.
By adding more.
How do we prevent that confusion?
By adding more to the name.
Okay. We could add more to the name. Instead of it being just Michael, Michael, and Michael, we could call them
Michael Smith. Oh, by their last name.
by their last name. Right? Or you'd be like, you're the teacher, Michael, and nobody else is. There's still 2 other Michaels that could also be easily confused.
AU works.
Okay? So we want to...
AU. AU.
Hey.
Right.
Okay, so we want to be able to change the names a little bit. The change in the names, as the title suggests, is referencing conjugate. Okay? So what we will do is reference the materials on the product side in quotes, so the right-hand side, because we're still biased left to right reading. We'll label those as the conjugates. So HSO3 minus is the conjugate. Wow, how do you spell? Yeah, I just lost track in the middle of there. H2O is the conjugate base. This now adds some clarity to it. So instead, or when I ask which is the base, you can tell me
Oh, I see.
SO3 minus 2. Now everything is crystal clear. If I ask for the conjugate base, you can tell me H2O. It allows me to differentiate the left-hand side from the right-hand side of the equation. Because depending on the perspective we're looking at, we would change our answer. Does that make sense?
Conjugate's always going to be on the product side.
The conjugate should always be on the product side. Okay? Admittedly, there is some, I don't want to call it a debate, because quite frankly, I think it's wrong. Okay? But in our old final, there was a question referencing this that I complained about and nobody wanted to change. Since I got to write the final this time, that question has disappeared. Okay? So we're back to this kind of clarity behind it. Okay? So with that, do the bottom one. Have you got questions? What's your question? Did anybody write that? What the heck? Come on, guys. Why'd you not write that?
Because it looks like the same thing.
Yeah.
What is different about this substance, HSO3 minus, than SO3 minus 2?
It's in the reactant side.
Charge is different, yep. So it's -1 as opposed to -2. What else is different about it? It has a hydrogen in front. But why is it? Yes? Why is it not an acid? What does H2O have in front? Hydrogen in front. Couldn't H2O act as an acid in this case? Yes. What becomes tricky about HSO3 minus? So what was one of our definitions of a base? Okay, we threw it in as the Lewis base. The Lewis base is donating electrons because it is accepting H+. What does SO3 minus have? SO3 minus have?
It's a negative charge.
What is a negative charge? Electrons. That species has electrons. Because it has electrons, it can act as a base. What did you all say it had? It had a hydrogen, which means? So which is it?
The acid.
Both. Can act either way. That directionality of it is going to depend on what it's reacting with and what we're saying those products are. Deciding which of those answers is correct is going to become very conditional. That condition is going to depend on stuff in OChem. What I want you to do is recognize your definitions, and based on what I saw, okay, we can go through and real quickly attempt to write this out again. What I believe I saw the class writing was this. You guys said it acted as an acid, so we ended up with SO3 minus 2 and H3O plus. Okay. Both of these answers are valid at this stage. Okay. So good. I saw everybody writing that. I'm super happy with that. That makes me, I don't know where I was going with that. That's good. Okay. The other thing that that species could do is act as a base, as I showed. Okay. So acids and bases aren't quite always super straightforward. Sometimes there's a little bit of complexity to it. That complexity we have to watch out for. HSO3 minus happens to be one that's a little bit more obvious, if you will, because we see the negative charge, which is a base. We see the hydrogen, which is an acid. So we could recognize both chemistries were available. Okay, kind of makes sense? Because that species is now special, because it can go both directions, we give it a special name. We call it ambidextrous. Isn't that far off. Amphoteric can act as both an acid and a base. Right. Some substances do that very readily, some don't. Just want you to be aware of it. Questions about what's up here? It looked to me like you guys have the acid-base definition down on lock, and you've got conjugates.
So in the bottom one, they have H2O as an acid. It's only an acid because HSO3 can be a base.
You're actually asking a little bit more complicated of a question than you think.
Oh.
Okay. The definition that you guys are working with acid is that you have a hydrogen in front and an aqueous in back. Would we ever write aqueous after H2O?
No.
Probably not. So within the definition system that you've got, you don't have a way of identifying this as an acid. Okay? Water does act as both. Okay? And that is a trickier statement. Okay? Okay. Okay. So, yep. Cool, cool, cool. Animate, animate, animate. So, the double arrow. That double arrow is referring to a concept known as equilibrium. Okay? Equilibrium is pretty much everybody's least favorite topic that actually has to work with it on the student side. If you're on the other side of the equation, being a researcher or an instructor, equilibrium is actually kind of neat because you can do some kind of cool stuff with it. Ultimately, what equilibrium is defining is a balance of reactants and products. Okay? it is an important enough concept that you spend an entire semester talking about equilibrium. So Chem 152, or second semester general chemistry, is devoted to equilibrium. So why are we talking about it in Chem 130? Because it's in our list on our competencies that we're supposed to talk about it. You're welcome. Okay? I disagree with that because it's a vastly more complicated topic than that. Okay? The biggest thing to tie to equilibrium is this concept of Le Chatelier's principle. Okay? Equilibrium. Equilibrium is a balance. Once a reaction has obtained a balance, what does it want to do?
Stop reacting.
Not actually stop reacting. Maintain that balance. Okay? Just like humans. Okay? If I had everybody stand up, get on one foot, and stand on your toes, you're going to start to wobble a little bit. If I came by and pushed you, what are you going to do? Fall, but eventually, what are you going to do? Get back up and attain the same thing, to obtain that balance. That constant oscillation you're doing to maintain your balance, chemistry is doing the same thing. Okay? But in the case of chemistry, we are taking two reactants, we mix those. So they were happy and at their own equilibrium. We now mix them, they do a chemical reaction to produce products. Okay? They're now standing up to achieve that balance. Okay? Once they're there, that's usually where we stop Chem 130. And that's where we would wait to Chem 152 to explain how the reactants and products balance out. Okay, so really what we're going to do within this topic is just talk about it through examples. So we had one example of just trying to stand balanced. Okay? And you do this with your life too. You do poorly on an exam, you're knocked out of equilibrium. What do? You try and do better on the next exam. You try and account for that and counteract that stress. Okay? So the first example that I like is a seesaw. Okay? In theory, people have seen seesaws. Again, we may be starting to reach an age category where you haven't seen seesaws because they're allegedly dangerous. Okay? But we've got a seesaw, a plank of wood, and we put a fulcrum in the middle. Okay? Little triangle that holds it up. Okay, if we put it dead in the middle, the plank stays stationary, right? Why do kids like this? Because what can we do? We can throw a kid on one side and a kid on the other, and you can now bounce back and forth, right? And it's cool because we're constantly moving out of equilibrium. What is the plank constantly trying to do? Balance itself back out. So it's trying to get back to equilibrium. We as kids are now taking advantage of the plank's natural tendency to achieve equilibrium because we keep messing with it, okay, so that we can bounce back and forth. Fun little game. Chemistry does the same thing. We have reactants and products on one side on each side. So once we run a reaction, it will go through and form some products. And I now have a balance of reactants and products. Okay, what Le Chatelier says is now that the chemistry is done, okay, and it's balanced, I'm going to mess with it. I'm going to mess with it by taking away some of the reactant. That is now gone. Would I be balanced anymore? So what does the reaction want to do?
The product back to the reactant side.
It needs to re-achieve balance. The only way it can do that is by taking some of the product and converting that into reactant. So it can re-achieve that balance. Kind of makes sense? So our reactions are constantly cycling back and forth between these two states. The problem with the seesaw is it's relatively static. Okay, we say we've achieved the equilibrium, now everything's done, and now we mess with it. Right? Did I have to remove reactant? Could I have done something else? Add more what? What happens if I add more reactant? We're going to cut a slice of that new reactant out and make a product until we re-achieve that balance between those. How to make sense? Okay. That would then seem to suggest the amount of reactant and product will always be the same when I run a reaction. would that be a particularly good reaction? What do you guys think? When you run a reaction, how much product do you want to make? All of it. So what do we want all of our reactants to become? Products. Well, if this is equilibrium, would I ever get all of it to be products? No. Okay, and in this case, the most I could get would be 50% of it converted. That's not really good. Okay? But in that statement, you're making one unfortunate assumption. At least one. Your assumption is that that fulcrum, that equilibrium, is located where? In the middle. Does it have to be in the middle? No. What happens if that fulcrum is located more to the product side? Okay. To achieve now that balance, what has to happen?
You have to put more product.
I'm going to have to convert more of the reactant across to product. Okay? So that I get a very tiny amount of reactant and a very large amount of product to counterbalance it. So depending on the equilibrium for an individual reaction, it could be a really good reaction. I get tons of product. Okay? Or, what else could happen? It could be a really bad reaction, and where does the equilibrium favor? Shifts to over here. Now what happens? Okay? I'd have a very tiny amount of product and a huge amount of reactant. So if I have a concept of the equilibrium for an individual reaction, I could look at that value, that equilibrium value, and say, that's not an experiment I want to run, because that's not going to produce a lot of product. Kind of makes sense? Okay, the other analogy, which is a little bit of a better one, we have two divided chambers, okay, with a little bit of a trap door down here. Okay, so we'll call one side the reactants and the other side the product. When I start a reaction, how much product do I have? Usually none. And the whole point was to make products. So I take all my reactants, I put them into my reactant chamber, and then I tell the reaction to do what? React. Okay, I'm giving them the opportunity to become products. Okay, if we're envisioning these as now liquids, what happens to the liquid? Okay. The reactant's going to drop down because it now has more space to fill. The end result is that I would end up with an equilibrium where they're now equal amounts. Does that mean no more reactant is becoming product? As in there's nothing moving between those two barriers, or those two chambers? No. There is still liquid constantly transitioning back and forth between those. We could observe that by adding a little bit of food dye. We add food dye to one side, what happens? The food dye will eventually dissipate through the whole system. So we're still constantly getting an oscillation of reactant and product. Okay? But the key point of equilibrium is that the speed for the reactant going to the product, so the speed forward is what?
Same as the speed.
The same as the speed backwards. Okay? Which brings in a new concept. This now brings in a question of rate. How fast does the reaction occur? Okay? Which is its own independent concept. 45. Sorry. Okay? So this is a better example because this brings in the idea of kinetics, okay, or speeds of reactions. Okay? And our equilibrium is when those two speeds equal each other. It's not static. They're constantly oscillating back and forth. So what happens if we now bring in Le Chatelier's principle? So Le Chatelier says we've let the experiment achieve equilibrium. Ta-da, here we are. Okay. I'm now at this point. But as a good chemist, I want to make more stuff. What could I do to my reaction to help more reactants become products? Okay, I can't change the rate of the reaction for an individual experiment. Okay, that's locked in. Okay, I heat it. What happens? The speed forward goes faster. so does the speed backwards. So heat does nothing to my equilibrium. How do I get more product?
More reaction.
So one option is add more reactant, just like we did with the other one. I've achieved my equilibrium, I add more reactant. Now what happens? That's going to shift across, and we're going to obtain a new equilibrium. Good. What else could we do? Changing the reactant chamber is a complicated topic that I don't want to cover yet, because that's effectively dealing with our equilibrium point. We're at our equilibrium. So we can't, for an individual reaction, we cannot change the equilibrium or our chamber size. Just like we can't change individual speeds of directions. I'm going to go through and say, well, once I've formed the product, I don't want it in the reaction anymore. So what I'm going to do is come up with a way to get a giant spoon or something. There's a giant spoon. Okay. Let's just give up. And I'm going to remove some of the product. By removing product, now what happens? It wants to equalize again. So what happens? The reactant will reobtain and shift to reobtain equilibrium. So depending on the individual reaction, I've got different techniques I could go through and do. I could try and remove product, okay, to adjust that, and that's probably the easiest one. Okay? Kind of makes sense? So, there was a suggestion about changing the chamber. Because even in this circumstance, we get an equal amount of each of those species. Okay? So, just like, I don't think I wanted to do that. Just like with the other case, okay, where we shifted the fulcrum, we can do the same thing with this chamber, except our argument now is going to be I'm going to change the location of my division. Okay? And depending on where I change the location of that divider, that's going to change how much reactants become products, because ultimately it's going to balance out. Okay? So we could still do that. Okay? That is changing the experiment, though. Every experiment has a defined equilibrium, just like every human has a defined equilibrium. Okay? Once we've established our experiment, we can't mess with that equilibrium anymore. It's always going to go back to and obtaining that. So I can remove product. It's still going to balance out so that the amounts of reactants and products match that equilibrium level. Make sense? Okay. So what affects the rate? Because that was a suggestion to look at. And the two chambers is the best one to look at. We've got the speed left to right, and we have the speed right to left. So we aren't looking at now balancing those. We're saying an individual speed, what's going to cause it to move faster from reactant to product or from product to reactant. There was one big suggestion that came out right out of the gate. Unfortunately, it's not the first one on my list. Temperature. Okay, and I'm going to get, oh, here, I won't guess. We'll say, nope, I have to guess. Oh my gosh, it's way at the bottom of the list. That was horrible. Temperature. Temperature is going to affect the speed of the reaction. That says temperature, trust me. What else could affect the speed of the reaction? Pressure is getting at a separate topic. One of the things that makes pressure difficult is when does pressure apply? Gases. What we're trying to do is reference all things. So let's back away from pressure and look at things that would affect pressure potentially.
What about the divider? Why that is?
So the divider isn't going to change the speed necessarily back and forth between those. The divider is now going to look at the relationship between the speeds. I want to know only what affects one speed.
What if the divider moves back and forth to kind of mix?
So remember, the divider can't move back and forth, so I know where you're going, but in this case, the divider is now locked into place. That defines our equilibrium. Okay? So we can't move the divider, but what you're suggesting is that what do I want to do to the reactants?
Mix it. Mix it.
I want to mix them. Okay? If I mix them, I increase the likelihood that those two things impact each other. Okay? And that's a complicated one. Yeah, we can call that the nature. I can accept that. The nature of the reactant. We will get back to your pressure one, I promise here. Okay, we just had too many other suggestions jump in. Okay? The nature of the reactant. Okay? Really what we're talking about here is the ability for the reactants to interact with each other. If I was taking solids and I wanted the solids to interact with each other, is mixing it going to do much? How many of you have tried to mix a pot of solids? Okay, it's not super easy, right? Okay, so what we're referencing here is, say, the phase of those reactants. If the phase was all in a liquid state or an aqueous state, then I could mix them. Okay, so the nature of the reactant becomes important, which is really referencing the phase, solid, liquids, gases, which oddly enough is going to get us back to the gases. Liquids are going to be fantastic for reactions because everything kind of free flows. What would you say about gases? Even better. Why would the gases be even better?
More space.
They're distributed evenly and mix even more uniformly than, say, even a liquid. Okay? So gases are awesome when we run a reaction. Okay? By that same token, they are also awesomely dangerous because they're going to free flow and move everywhere. So if you have an open container, where are those gases going? Everywhere into your lungs. That's not generally a good idea with chemicals. Okay? So the nature of the reactant is an important one. So back to our gases. So there was a suggestion about pressure, and I complained about pressure because pressure is too specific to gases. What could I relate the pressure to that would also allow me to bring in the other phases? Okay. Volume kind of works, but again, the volume is more important for gases. Interestingly enough, in Pivnert, what was the T? Temperature. Already on our list for speed. What else shows up in Pivnert? Comes after M. N. What was N? Moles. What are the moles? The amount of the substance. Okay? What are the odds that you will find a successful partner in life? Okay, right now you're like, I don't know, there's a lot of people out there. You are the last person on the planet. 0. Why is it now all of a sudden 0?
You're the only one.
You're the only one. You're not going to find another partner. Okay, unless you have a very fancy mirror. Right? If there's another person on the planet, what happens?
You have no choice.
You have a shot. Okay?
No choice.
Okay? You have no choice, but you at least found there's the potential for a partner. Okay? On the planet. So if we change the amount of the substance, we can improve the odds that the reaction actually happens, that you find a partner. So that's effectively what's happening in chemistry. We're trying to get two chemicals to interact with each other. Okay? So the amount of the substance is important. Okay? Well, is there something else tied to amount that is also important? Kind of from Pivnert. What if that, so you're the last person on the planet, you are locked in this room though, and the other person is locked somewhere else? Well, your chances go back to 0. What happened? Nature of the reactant. Okay? Those reactants can't mix. What if they're locked in the room with you? There's a chance of mixing. Okay? Why is the chance of mixing now better than if they were just somewhere on the planet?
Because you're in closer proximity.
Closer proximity. What are you referencing with that closer proximity? Not only the amount, but also the volume. And in particular, what happened to your volume? If volume gets smaller and the concentration goes up, or the amount goes up, your end result is something goes up. What is that something? It's not density because it's for an individual substance, but you're getting at the right idea. This would be a concentration, also known as molarity. Okay, so concentration becomes a really important effect in a reaction. So if I want a reaction to go faster, what might I do? Increase the concentration. I want those things as concentrated as possible because now they can interact with each other. Okay? Nature of the reactant. I may put them all into the same phase so that I can increase the likelihood that they do interact. Because even if I have a high concentration, I can take a solid, that's as high concentration as I get, and another solid. Both of those are insanely high concentrations. But the odds that the two would react with each other become very limited because the only place they can interact is on the surface. Okay, so by getting them into a solvent, I can open that up. Okay? What else could we do to help increase the odds of you finding a partner? Blind dates? How do blind dates get set up? What's that? By a third party. A third party says, hey, I know you and I know you. You'd be awesome together. You meet each other. It don't always work, but you know. What did that third party act as? An intermediary to speed the reaction along, to speed that process. They're acting as a catalyst. Okay? The last one, trying to come up with relationship comparisons, and I'm trying to be somewhat nice about it. Your first date is a dinner or coming to one of my lectures. Like, why the hell would I go on a first date to Mike's lectures? I'm an awesome catalyst, man. Which of those do you think would be more likely for a successful interaction?
Anything but the lecture.
Anything but the lecture. Don't trust my skills. The interaction of how that thing goes about or how that reaction happens affects the speed of it. Okay? If you try to date someone just by coming to my lectures with no other circumstance, you're limiting the speed of that. If you can increase the interaction outside of the lecture, you can potentially increase that interaction. Make sense? So what we're talking about in that circumstance, in chemistry terms, is a mechanism. How does the reaction happen? Okay? So when we talk about our rates, we've got these 5 things. Concentration, the amount of people on the planet, okay, which will also include the volume. Okay? So I want a large amount of people, and I also want it in a very tiny volume. Both of those are things that contribute to concentration. The nature of the reactant. Okay? I want them to all be in the same phase so that I can increase the interaction between them. Okay? Larger surface area. Okay? Have you ever tried to burn a log of wood? Okay, it takes a little while, right? What if you took that same log of wood and put it into sawdust and then tried to burn it? It burns faster. Why does it burn faster? It's the same amount of wood, but there's more surface area. Okay? That's effectively putting it into solution. Mechanism. How does the reaction proceed? Okay? In chemistry, our reactions proceed through what is effectively known as collision theory. Less nicely, this is if you attempt to do anything in the world, and we could really make this one awful, trying to find a date by just walking around blindfolded and bumping into people. Hey, do you want to be my partner? No? Okay. Okay. That's what chemistry is doing. There is no mind, there is no eye of our individual molecules. They just fly through the air and hit something. If they hit it hard enough, whoop, there's a chemical reaction. Okay. If they don't hit it hard enough, no chemical reaction happens. Okay. To get an idea of how difficult that is, you can take a pen and just blindly cap it. Well, I can feel where the things are. Okay? Put on mittens so you can't feel where the things are and then try and cap the pen. Right? It becomes a little bit more challenging. That's what chemistry is trying to do. Right? That's one of the things that's so phenomenally interesting about it, is that all this stuff is going on and it's just smashing stuff together. Okay? Temperature, directly related to the rate.
I just watched an episode of 99,
Okay.
Smushing Butts.
Temperature is also directly related to our rate. The hotter things get, the more likely they interact. If we go back to the smashing things together, the hotter things get, the faster things move, the more likely they collide with enough energy to do a correct interaction. Okay? And then the catalyst is just a third party to help those two things happen. Okay? This is why biology is cool, because we exist not just of random smashing together, but there's something that our bodies have developed over time that facilitates those reactions happening. Okay? Those are our catalysts. The catalysts are not consumed in the overall reaction. That does not mean at each individual step through the reaction they aren't destroyed. They must be reformed by the end of it. Okay? So, how does this apply back to acids? If we look at water, water is a relatively even balance. In fact, if anything, it's kind of horribly drawn there. Water, whoa, that was supposed to be an eraser for this part. If we look at water, reactants to, say, products, okay, forming that H+, our equilibrium pretty heavily favors the reactant. So we get a very small concentration of H+. Okay? What happens with, say, something like HCl? What is HCl? Hydrochloric acid. Okay? As an acid, what does it do? Gives off lots of H+. So I get a huge concentration of H+. So if I look at the equilibrium for H+, I would see a lot of product, very little reactant. Okay? So what we'd be referencing is that equilibrium. Because figures can be a bit daunting and messy to deal with, what we want to do is come up with a numerical definition or a numerical system for this. Okay, so number one, equilibrium, I want a symbol. What would be a good symbol to pick for equilibrium?
E.
K, I completely agree with you. E was already taken, energy. Okay? So we're going to define our equilibrium by this K value. That equilibrium is a constant. It always stays true, and every reaction is going to obtain its own K constant. Okay? That K constant is defined by the amount of products in relationship to the amount of reactants. So if I look at the K constant for water, what kind of value would I expect to see? A big number?
No, small number.
The amount of H plus is very, very small at our equilibrium. Our H plus is our products, which means the K value for water ends up being a very tiny number. Okay? So tiny, I choose to use powers of 10. And I get 10 to the negative 14. Really, 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 really tiny. If I use HCl, what happens to my K constant? Okay? Product concentration, the H plus is very, very high. The reaction concentration is very, very small. I get a K value that is very, very large. We're looking at something, and this one I actually don't know off the top of my head. 10 to the, let's say 3. Okay. Most Ks for reactions are 10 to the negative value. Okay, so relatively small Ks. Okay, not 10 to the negative 14. Okay, but 10 to the negative 2, 10 to the negative 3. They sit somewhere around that 1 value. Okay? Some reactions, we get very, very large Ks. Okay? How many of you like dealing with powers of 10? Okay, 2 people. So powers of 10, not so fun. So while I could reference the strength of an acid based off of these K values, that becomes a bit challenging for me to manipulate and to deal with. So I try to develop a new system for it. Okay? The new system that we end up looking at, okay, or one potential new system, is just strict memorization. I define my strong acids completely ionize in water. As you learned last week, these would be strong electrolytes because they form lots of ions. The weak acids and bases ionize to varying extents, so different amounts. That's 152. How would I differentiate between them? Okay. I would memorize. Your strong acids, there's, of course I only listed 6. There's 7 that, depending on your instructor in 151, they may make you memorize, they may not. Okay. But if it is one of those strong acids, anytime you see it, you know it completely ionizes. Same kind of thing happens with our bases. Okay? There are certain compounds, remember our bases, we're going back to the Arrhenius definition, hydroxide, completely ionize when they hit water. What substance would completely ionize with hydroxide? Meaning we go back to our solubility rules, and in our solubility rules, what things would always be aqueous with hydroxide? Really just our group 1, but also our group 2 sometimes. Okay? There's some weird exceptions within the group 2. Okay? Those 2 things will always be ionic, which means strong bases. They're completely ionizing. So the strong term just means ionize completely. The weak term, well, how would I know it's weak? It's not strong. That's it. Okay? Defining how weak, save that for 152. Okay? So dealing with our powers of 10, okay, we could look at concentrations if we were trying to deal with safety and tell people to watch out for certain concentrations of acids. Okay? That gets a bit challenging because probably none of you have heard a molar before this class, or 2 or 3. So that's not very useful. No one's heard of that. Okay? So how could I adjust that? Define a new system that embeds the information of the concentration into a different unit system. pH of solutions. The pH of solutions incorporates concentration into it. Except instead of dealing with powers of 10 or equilibrium, we get pHs going from 0 to 14. Where very low pHs and very high pHs are bad. Because a low pH is acidic and a high pH is basic. Right? Ideally, we sit right in the middle at pH 7 being okay. Okay? How do we solve for a pH? Okay, it is the negative log of the concentration of hydrogen ions. So all I have to do is determine the concentration of hydrogen ions using my equilibria, and then take the negative log of that value. Anybody see any problems with that? There's a log, and there's a negative sign. Both of those things together make dealing with pHs and how they relate to equilibrium virtually impossible. That's why we spend an entire class talking about it in 152. Okay? What you're responsible for is recognizing the useful levels on that scale. pH 0, acidic, pH 14, basic, pH 7, neutral. We've got, I think, literally 1 slide left, and then we'll do that on that other day. Today's Tuesday, right?
Yes.
Thursday. So the plan on Thursday